So I will be talking about advancing full tensor magnetic radiometer squid and also UAV magnetometer gradiometer systems, and especially in the context for diamond exploration. Maybe just right before I start, I need to acknowledge some people were pivotal and played an instrumental role in the projects I will be showcasing today and will be talking about. And I would want to especially recognize Louis Polomé from Spectrum Air, David Pratt from Tensor Research, who are both co-authors to this paper, and also Ronnie Stolz from IPHT, who all played a big role in the technology and innovation we'll be talking about today. So in our search for primary diamond deposits, De Beers relies heavily on airborne magnetics as the principal method to discover new kimberlites, and it's always the first method we would be flying over new ground. With the advent of full tensor magnetics and a shift to vector measurement, it really provided us with a unique opportunity to introduce a paradigm shift in the way we acquire our data, how we model our data, and how we interpret our data. I just need to get to move it on. So if we look at what we're actually looking for on the kimberlite side, kimberlites are generally small pipes of very subtle signatures, especially difficult to detect in magnetically complex terrains or geological complex terrains. And it's always important for us to try and understand that the signatures in terrains that's difficult to access often host very prospective ground, and that we need to try and find that. The kimberlites are also, the ore bodies are geologically complex, consisting of varying internal geology and often with multiple lobes that has been intruded at different times. On the physical property side, I think the one factor that really stands out is remnants, with more than 80% of kimberlites having very strong remnant magnetic signatures, making it a key differentiating factor when we are looking for kimberlites and to select targets. Since full tensor magnetic squid surveys provide extremely sensitive measurements of the Earth's magnetic field, and the tensor components have significantly more resolving power than normal TMI, detection and selection of targets in geological complex magnetic terrains can be improved. So what started out as a project with IPH2 in the late 2000s to develop squid sensors for airborne systems quickly evolved into a program where we start looking at developing new squid platforms, looking at enhanced gridding techniques and visualization for tensor data, enhanced 3D modeling and automated modeling interpretations, deriving gradient tensor components from the airborne TMI, and also collaborate with a number of research groups in terms to develop optimal parameters for full tensor surveys, looking at machine learning for automated anomaly picking and geophysical surveys, and also have a bit of a stab at UAV platforms. This is just a quick reminder that the magnetic gradient tensor has desirable mathematical properties that simplify interpretation. Maxwell's equations imply that the tensor is symmetric. It's also traceless, and that means that 5 of the 9 tensor components are linearly independent. The eigenvalues are real and are rotational values, and because it's a true potential field, it can be upward or downward continued using standard techniques. Each of the directional components or tensor components you do see on the right-hand side represents a directional filter that emphasizes structures in specific orientations. A little bit closer to home, this is just a pipe-like signature of a piper body showing the different tensor components. In the bottom left, we have the TMI, and then the components. And I think the two components that stands out the most is probably the BZZ in the right-hand corner, which is a negative, and in the center, the BXY, which is a quadrupole, which is very specific characteristic of pipes in the tensor data. So maybe just quickly touching on why we want to use the full tensor squid surveys for diamond exploration. It provides us with extremely sensitive full tensor measurements of the magnetic field. It provides improved resolution to detect small and very subtle anomalies. The tensor components have significantly more resolving power than a TMI. With regards to remnants, the mapping of remnants indicators increases diagnostic physical property information. It actually added another dimension to the data interpretation. And it allows us to differentiate between similar intrusion, structural, and alteration events. And in terms of inversion modeling, the joint inversion using all 60 channels enables improved modeling, and it also reduces ambiguity and non-uniqueness of potential field data. So all in all, the improved data quality and modeling, the better prioritization of the targets, fast execution of work programs, and reduction in exploration costs due to less drilling because we are selecting better targets is the main reasons, or are the main reasons why we are focusing on this. This is just a quick update on the status of the current system. Or systems, the DS and Anglo American do have a helicopter system operational with tow birds for both the horizontal cryostat system and the vertical cryostat system. Noise levels are in the region of 10 picotesla per meter, and these systems are managed by Spectrum Air. You might recall at the SAGA meeting in 2024, I've spoken about the development of a fixed wing system that was in progress at the time. That is shown in the bottom, with the horizontal cryostat mounted in the larger stinger at the front, the altimeters and flux gate in the back. And then we've also added 2 cesium magnetometers to the wingtips on both sides to acquire long wavelength total field data that could be integrated into the data and allow us to with the modeling of the deeper bodies. I also mentioned at the time that our biggest challenge in developing a system was not a technical challenge, but it was to get regulatory approvals from a civil aviation authority to make the modifications required to the aircraft. Ultimately, it turned out that new requirements from the CAA could not be fulfilled on our side to get the approvals for all the changes that need to be made to the platform. And unfortunately, this project was cancelled in 2025. Just quickly touching on some of the operational challenges we are facing in the field. And the main challenge is obviously the handling of liquid helium, which is required to cool down the cryostat to 4.2 Kelvin, where the sensors become superconductive. Liquid helium is not always readily available. It's difficult to transport and to handle in the field with the filling of the equipment. So this is a bit of a logistical constraint we do face. And the liquid helium is also not relatively expensive. So moving from acquisition systems to the way we grid and visualize our tensor data, it's important to remember that the tensor components are interdependent and traceless. And in order to protect the data integrity, the tensor processing and gridding techniques need to be applied in a tensor consistent manner. And since the full gradiometer, the data is very highly sampled and less influenced by spatial aliasing, it can also be gridded at much smaller cell sizes, which contributes further to the improved data resolution. Gerald and Intrepid has been at the forefront in developing new proprietary algorithms for the gridding of full tensor mag data, which really deliver superior results, including SLIRP, which is spherical linear interpolation, where instead of a normal 4 cells between flight lines, you can now use up to 8 cells that's supported without any significant aliasing. To demonstrate the benefit of the tensor gridding, the 2 images on the right, which is looking at the the same data set, but gridded with the different techniques, you can clearly see the benefits. So on the top, we've got conventional gridding, minimum curvature gridding, and at the bottom, it's the data gridded with the Intrepid tensor gridding routine, and obviously at a much finer cell size. So I've spoken about aliasing, and that's an important parameter when you look at survey planning. I want to touch a little bit more on that. We all remember that buggy wheels turning back, sometimes turning back in the old movies. It's a great example of aliasing and undersampling. And just to illustrate a bit further, the profile on the right-hand side, the top profile with the 100 sampling points is fully adequately sampled and the true representation of the signal, or the profile at the bottom with the long wavelength and only sampling with only 5 sampling points is obviously totally undersampled and alias. And this results in the incorrect characterization of the profile data in erroneous interpretation. So we have been working with tensor research to develop a method to analyze aliasing in aeromagnetic surveys through an experimental approach. And Dave Pratt has designed a theoretical model on the left, and that consists of 72 circular pipes, elliptic pipes, and ellipsoids of various sizes. The line data was sampled at different line spacings and then gridded with different techniques, and it was compared with the original theoretical grid that was computed from the model. The aliasing algorithm provides us then with a statistical tool to compare the effectiveness of the different gridding techniques. And in the examples on the right, we are comparing aliasing of data gridded with conventional minimum curvature techniques versus aliasing of tensor data that's gridded with Intrepid's tensor gridding algorithm. So the dashed line that is currently shown represents the aliasing results from the minimum curvature gridding. You do have the alias power plotted on the y-axis with the center height on the x-axis and the different colored lines representing different line spacings. So the two top graphs show the BZZ and BXX grid aliasing for a 50 diameter pipe that is centered on the flight line, while the bottom two graphs offer the same pipe, but this time 50-meter offset from the flight line. And you can clearly see the increased aliasing. So if you look at the aliasing results from the tensor gridding that's shown now as the solid lines, you will immediately notice the significantly reduced aliasing, especially when the body is offset from the flight line, as shown in the bottom two graphs. So the takeaway here is basically that the inherent 3D information from the measured tensor components can significantly decrease the amount of aliasing. And from a data acquisition perspective, that is important. It provides clear evidence that for full tensor surveys, where the tensors are measured, can be flown at a much wider line spacing than conventional surveys, and without significant aliasing and without compromising any of the data quality. So this is just a case study from Canada, where the survey was flown at 50-meter line spacing and a 35-meter bird height. The quality was exceptional. The noise levels were generally below 10 picotesla per meter, and this data was probably one of the best data sets we have acquired. So you do get a number of products you can derive from tensors. That's very useful in interpretation. The normalized source strength is a parameter that's very useful in the study of permanently magnetized sources. It's very similar to the analytical signal. Because it peaks directly over the sources, and it's largely independent of the magnetization direction. You also do get invariant quantities that exist at a higher resolving power than the analytical signal. The invariant I1 in the middle outlines source boundaries, while the invariant I2 preferentially outlines shallower features of complex sources. So this is just a couple images showing some of the results and how we're using it. In this case, we've just plotted the resultant magnetization, which is a remnants indicator. Here we've got pipe-like bodies that were identified through the semi-automated modeling techniques, and here's the estimation of the depth to the top of the body for the survey area. This is normally the final product we get. This is the structural model of the whole survey area, and in this case, it has been color modulated by susceptibility. So I've shown several products was derived from the modeling of the tensor data, but I would like to touch a little bit more on the modeling process that we are following. So Tensor Research has been collaborating with the BS and Anglo American over the last decade to develop bespoke semi-automated multi-stage inversion and interpretation software for full tensor data. And that software aims to build a 3D regional rock property and depth model of the geology at unconformity surface. This is just looking a little bit more in terms of how we're using it. So the semi-automated methods use the line data and the inherent 3D information that's contained in the tensors to create a model segment, and that is using through parametric analysis of the data. So for every magnetic anomaly on every line of the whole survey area. Okay, so those segments are then linked together. Let's assume that in the second image, and to build a 3D geological model, and that model is then used to constrain the joint inversion of the full data. This is just some of the data or geological information that we can derive from the tensors. So the normal source peak, which is at the center when you've got the narrow target shown on the right-hand side there, and it's on the edge for wider targets. You can identify dimensionality of target style, strike azimuth, susceptibility, inclination and declination both for pipes. You can get an indication of the depth, and you can also get this structure index indication. So until now, I've focused on full tensor magnetic gradient data that's acquired by the full tensor magnetic squids systems. But I would also like to talk a little bit about the use of mathematically derived tensor data. So since TMI data closely approximates a potential field, the magnetic components can also be derived in the frequency domain, given that you have sufficiently dense sampling data. So to ensure that you have data that's well sampled, that you can use to transform the TMI data to the gradient data, there are generally two rules or two guidelines that one needs to keep in mind. The first is from Reed, that recommended that the alias power for total field surveys, where the data will be used to create gradient maps or vertical derivative maps, that should not exceed 5%. And that basically implies that the survey line spacing should be equal or smaller than the height, and that height is the distance between the sensor and the magnetic source. Dave Clark later extended Reed's approach to the gradient tensor for poles, quadrupoles, and basically for poles and quadrupoles. And I will be focusing at the moment just on the point pole, which is representative of the narrow vertical pipe-like bodies. So the point magnetic field fall-off rate of the point pole with the vertical body is 1 over r squared, and the gradient tensor fall-off rate is 1 over r cubed. Dave's graphs is shown on the right-hand side, and the red line on it denotes the 5% alias power cutoff, while the solid black line represents the pole or the dipole model. So the results basically indicate that the line spacing of less than 0.8 times the height or distance between the source and the sensor is required for the BZZ tensor component, so that the earliest power does not exceed 5%. And this is basically a rule that we use quite often in the BS, and we're trying to keep to that rule when we design our surveys that we want to use to transform to TMI data or to gradient tensor data at a later stage. There are some constraints with the measured data, obviously. So the calculated gradient data will be at a much lower resolution than the measured squid data. And that is because the squid sensors are order of magnitude more sensitive than the cesium vapor sensors. And also the tensor grids are mathematically derived from a TMI grid. It's not derived from line data. So and that process delivers longer wavelength, smooth tensor data with reduced resolution compared to measured data. And I think most importantly, most of the diagnostic information of the tensor data resides in the high frequencies. And those are often lost during processing of TMI data and through leveling, micro-leveling, heading, and low filtering or low-pass filtering corrections. But despite this, there are still a lot of cryptic information contained in the tensor data, which is very useful and which was not available previously, and data that could add a lot of value to exploration programs. So we now routinely actually transforms our TMI data to adequately sampled and high resolution high resolution TMI data to the gradient tensor components. And this is just an example of such transformation. This survey is a fixed wing gradiometer survey that was flown at 75-meter line spacing and 30-meter height. The overburden is 120 meter. And the aliasing in this case was actually, because of the tight line spacing, the aliasing was less than 2%, which is actually great. So this is just an area I would like to focus in a little bit more in terms of interpretation. So this is just an example of how we're using the data to interpret. This is the TMI contours background that's overlaid by the regional modeling solution derived from the tensor modeling, and that's color modulated according to susceptibility values. The red annotations above the bodies denote dimensionality index, and a very good correlation is observed between the pipe-like bodies and the actual kimberlite positions that's marked by the yellow triangles. So these two images just shows some of the geological models derived from a larger survey, with the model on the left showing the remnant magnetic signatures highlighted, and a model on the right being color modulated by susceptibility. I think it's important to remember that during the Fourier transformation of the TMI grids to the gradient tensor grids, the IGRF field direction remains unchanged, okay? And the inherent remnant information is retained in the tensors. And because most cumuli are remnantly magnetized, as I mentioned earlier, the ability to extract remnant information at an early stage of an exploration program plays actually a key role in differentiating and prioritizing anomalies for drilling. Geophysical modeling solutions, as you all know, are often non-unique, and it's with dissimilar bodies potentially displaying same data profile. So in the bottom, I've got two data sets, same data sets. But because the magnetic tensors provide more diagnostic information and the joint conversion of the gradient tensor components, it often helps to resolve non-uniqueness and reduce ambiguity. So what we're seeing here is that the 6 tensor components in red, and the model tensor component does not match the actual signature for the 6 pipe-like bodies on the left-hand side, the circular bodies, indicating that the circular pipe model are incorrect. You will actually notice from the bottom, from the TMI data, that data fits the TMI data pretty well. And then those 2 linear data bodies does actually fit the model data, and the actual data fits very well together on the right-hand side, indicating that's a correct solution in this case. So just with regards to emplacement agents, it's actually quite an important thing in exploration because it does have some economic implications, and we're using the method published by Dave Pratt in 2013, and we demonstrated the use of magnetization vectors to determine emplacement ages. So the process is basically to determine the great circle, which is the plane on which the magnetization vectors lie. Then you plot the polar wander path and the intersection of the polar wander path with the great circle provides the indication of the emplacement age. In this case, the emplacement age of 78 million years from Botswana example correlated very well with the age dating derived from the zircon dating. Moving to the use of machine learning, this is an example of a collaboration with Jaja Sun and Keenan Barker from the University of Houston, where they used deep learning to detect kimberlite pipes. The method employs convolutional neural networks that treats the full tensor components as the multi-channel inputs, and it aims at finding a mapping function between the tensor measurements and the location of the kimberlite pipes. This is just the actual example of the data, and 91% of the anomalies selected by PS geophysicists previously were also predicted by the unit from their method, with the correctly predicted peaks denoted for white cross and the incorrect peaks in black. So there's a very good correlation, and that provides us a great promise of using these methods going forward. All right, getting to the close of the presentation now. To transform the TMI data to tensor components, it's essential to acquire high resolution data, and UAV magnetic gradiometer systems with real-time sensors on board and provide really superior quality data. And it's very well suited for computing magnetic tensor data, especially since the UAVs are normally well sampled, the data. It's flown close to the ground at very tight line spacings, and that minimizes aliasing issues. We have also noted in all the work we have done with the tensors that gradient enhanced data is superior to normal TMI data for the transformation of two tensor gradient components. And the reason for that is the gradient enhanced data contains inherent information that's not contained, or inherent cross gradient information, I should say, that's not contained in the normal single sensor data. So the DS acquired this flying cam discovery helicopter system to advance its objective of acquiring optimal high resolution geophysical data across our exploration pipeline.
Can I interrupt you? So it's actually 4 minutes left because...
Okay, I'm going to take less than that.
Okay, good.
Fine, thanks very much for that. Okay, so in this system, I do have a gradiometer option that we have been collaborated with Flying Cam to develop. It's got a turbine engine with a 2-hour endurance, a 50-kilogram payload that really makes it well suited to fly medium-sized magnetic surveys. So a standard high altitude calibration flight over quiet magnetic areas, that's standard process with normal airborne surveys, are not feasible for UAVs for obvious reasons. Of course, they're not allowed to fly that high. And the calibration maneuvers suggested by both TOC of 2019 and Rehego is that you should be flying over low gradient areas at the maximum allowed height in either hovering, which is just a normal hovering mode and just moving around, or in full box mode, and then that should be completed several times, and the result of that is compensation. The results of that is pretty good. So the current status of this system, it's still in development, and it has been impacted by both business and operational considerations. And there's been a very long process that's actually still ongoing to get CAA approval for this new helicopter platform. It is the first helicopter platform in South Africa that's used for that, and it is a protracted process to get the system approved. So we've not flown any surveys in South Africa because it's not been certified to fly yet, but we did do a couple of test surveys in Belgium before the system was shipped to South Africa, and that's where I got the performance figures from. Okay, so in conclusion, the full tensor magnetic gradient service provides exceptional quality data that's very well suited for kimberlite exploration and to detecting small subtle signatures, especially in geological complex magnetic terrains undercover. Okay, the SQUID service can be flown at a much wider line spacing than conventional airborne surveys. And the measurement of a magnetic, full tensor measurement of the magnetic fields allows the application of new filtering, gridding, modeling, and visualization techniques that really greatly improve the information and resolution relative to data acquired with standard sensors. Extracting spatial and magnetic properties, mapping down conformity service, building 3D geological models for magnetic tensor data through semi-automated modeling, improve our target selection, and also enables fast execution and exploration work programs and leads to reduction in exploration costs. And then lastly, transforming high quality, non-aliased, high resolution TMI grids to gradient tensors and provide a viable tool to extract more information from both conventional and historic airborne magnetic surveys, given or assuming that they are of sufficient high quality and resolution. And there's just a number of acknowledgements in here that for many people that worked on many of these projects over the years and really contributed towards the success. And thanks very much.
Perfect. Thanks so much, Anre. If anyone has any questions, feel free to raise your hand. If